Welcome to our third video on acid-base chemistry and acidity. In this video, we'll be looking at more structures to keep learning more about the kinds of structural features that will actually impact the acidity of compounds. So to do that, we'll work with these three acids that are shown here in this column. And because we know that the structures of conjugate bases are very important for understanding differences in acidity, I've also drawn the conjugate bases of our acids. And then finally, I've given you the pKa values of the acids themselves. So this looks a lot like the exercises that we did in the previous video. But here we've got some different kinds of structural variables. It's always what we want to start with. So we'll notice that there seems to be a conserved functional group in all three of our acids. And that's this oxygen-carbon-oxygen-hydrogen unit, which is here, here, and here. And so we know that that unit, that so-called carboxylic acid functional group, can't be driving differences in acidity. It's the same in all of these structures, right? But we do have differences structurally on the left-hand sides of the molecule. So we've got a methyl versus what's called a chloromethyl, and then this chlorine group on the outside of these two different carbons away from the carboxylic acid. So you can see the acidity trends here. And it's really important to me that you start to actually look at these variables, look at the trends, and see if you can come up with some kind of an explanation. This is really good practice for conceptual reasoning, which you'll be doing on homeworks and midterms. So I'd like for you to actually take a stab at this. Right? Pause your video and come up with a hypothesis, some kind of explanation for why you're seeing the acidity trends that you do, given the structures that you see for these conjugate bases. So you've had a chance to write your hypothesis down. Remember that it doesn't necessarily matter whether your hypothesis ends up being right or not. The idea is that you're looking at these structures, thinking about what the framework we're using is for assessing acidity, and then seeing whether we can fit what we're observing about differences within these structures into that framework. So to do that, I'm going to go ahead and start by just pointing out the differences again, but I'm going to focus on the conjugate base structures because I know that that's what's going to drive things the most. So what I'm noticing in particular is that this compound is missing a chlorine entirely. So I've got no Cl. On the other hand, here I've got a chlorine atom. And in this structure, I have a chlorine atom as well. So one way I could parse this is no chlorine versus yes chlorines. Okay. And it looks to me like if I have a chlorine, that I'm more acidic than if I don't. Well, that tells me something. That this conjugate base, out of the three available, is the least stable. I'm going to abbreviate conjugate base as CB here so I can fit it on the board. And so that I've got kind of an observation that I want to write down, or a note. It seems to me that having a chlorine somehow stabilizes the conjugate base. Just on the basis of these three conjugate base structures and the corresponding acidity data, like these two structures seem to be more stable than this one, and that's what the pKa's are telling me. Okay, this is one of the reasons why pKa's are so useful. They tell us something really intrinsic about structure, right? Okay, but it's not like having a chlorine is like a yes or no proposition. It seems to me that like where the chlorine is also matters, because there is a difference in acidity between these two structures. It's not a big difference, about 1 pKa unit, which is 1 order of magnitude. Remember this, pKa is negative log base 1. But certainly a lot smaller in difference than we were seeing in the previous video where we were talking about differences like 50 pKa units to like 14. So chlorine stabilizes our conjugate base, and also we can say the position of the chlorine matters. So when I'm thinking about the position of the chlorine, I want to talk about its relationship to probably the part of the molecule that's undergoing the largest structural change, and we're going from the acid to the conjugate base, and that's going to be the new lone pair. So we actually talked about that at length in the last video, that we were assessing, for instance, like the electronegativity or the atomic radius of the atom that's gaining the lone pair, losing the hydrogen. And so at least here, I have oxygen versus oxygen versus oxygen. So those are factors from the previous video. They're not going to be relevant here. But if I'm trying to talk about what the chlorines are doing, and I notice that position matters, I might start to think about, well, where is the chlorine relative to this atom that's essentially building up electron density? One thing that I can notice is that this chlorine is like closer to this oxygen than it would be the case here. So this is closer, this is further, and that tells me something else. The position of the chlorine matters. Apparently, if the chlorine is closer to the oxygen, then that gets me more stabilization than if it's further away. So I can have like a, I guess, a subnote, Cl closer to oxygen, gaining a lone pair is more stabilizing. So here I want to call out closer and more. Those seem to be connected to each other, right? The closer I get, the more stabilization I get. So what's left for me to do now is couch what we're learning here in our observations or notes into this framework for understanding conjugate-based stabilization in a first principles way. So in the previous video, we talked about things like minimizing electron repulsions or trying to put electrons close to atoms to which electrons are attracted, right? Those are concepts about like electronegativity or atomic radius. It's not clear to me exactly how we're going to use that because this lone pair that we're gaining onto the oxygen, it's not actually like on the chlorine. On the other hand, this does look familiar with some kind of concept that we've talked about before this semester, where the proximity of an element like a chlorine atom or something else that's highly electronegative influences electron density. We saw this in NMR. This was induction. So maybe we're seeing some kind of an inductive effect influencing acidity. All of these things seem to be consistent, especially this concept of closeness or proximity. We saw that induction was kind of very sensitive to that. And that's true. So what we're observing here is that inductive acceptors, so elements or groups of atoms that will actually exert a pull on the bonds that they have to a molecule, are going to stabilize buildup of electron density. We call this our inductive effect. All right, so in these two structures, the chlorine atoms are inductive acceptors. And the idea here is that even though this lone pair on oxygen doesn't actually get onto the chlorine atom, the chlorine is creating this ripple effect, where the electrons in the chlorine-carbon bond are going to move a little bit closer to the chlorine. And so that makes this carbon, relative to the case where there was no chlorine, kind of partially positive. And that makes this carbon-carbon bond a little bit polarized also. Here's the ripple. So relative to the case where there was no chlorine, this carbon is also going to be a little bit positive. But now we're starting to diminish the effect, and that makes this carbon-oxygen bond a little bit polarized in a different way. So we know that most of the time the electrons in a CO bond are going to be very close to the oxygen. But if I make this carbon a little bit partially positive, the electrons in this bond are going to move just a little bit toward the carbon. They're still going to be closer to the oxygen than carbon, but less close to the oxygen than if the chlorine was missing. So it's kind of a complicated idea. Think about the electrons normally residing really close to the oxygen. The influence of the chlorine is to pull them back just a little bit into this carbon-oxygen bond. And what that means is that the electron density that's very close to this oxygen is diminished, right? So we've got these three lone pairs and the electrons in the CO bond. This inductive acceptor takes the electrons in that CO bond and moves them a little further away from the oxygen. Well, that relieves some of the electron repulsion at the oxygen and stabilizes the conjugate base. So as we stabilize the conjugate base, we know that the acidity of the corresponding acid should increase, and that's what we see. That also, this invocation of induction also helps us explain why moving the chlorine atom further away from the oxygen is actually going to lead to diminished stabilization, because now there's a larger number of bonds that have to be essentially, we have to travel through, if you will, to actually influence what's happening nearby the oxygen where the charge is building up. So we still have an inductive effect here. It's just a weaker effect. Okay, so basically what we're seeing is what you already know about induction. All of the rules that you've learned about induction, they apply directly to acid-base, or really acidity, right? Predicting the relative acidities of molecules. Here we're seeing proximity. You know that there are other kinds of concepts that also are important for induction. And basically how we can knit together your understanding of induction with your understanding of acidity is that induction is going to essentially remove electron density from a position where it's building up, that's stabilizing, and that's going to increase acidity. So what I'd like for you to do to reinforce the connection that you're making between induction and acidity is to draw the structure of a carboxylic acid. So you'll keep this part of the molecule, but change this part so that you have an acid that's even more acidic than this compound. So a pKa that's lower than 2.9. And to do that, think about induction and how that will influence conjugate bases. This will take you a couple of minutes. Get creative. If you need to go back and review induction in the NMR videos or in your notes, that's fine. But I want you to really truly draw a structure of a compound that looks like a carboxylic acid with something over here that's going to make the carboxylic acid more acidic than this particular structure. So you get a chance to draw your structure, and it turns out that there are lots and lots and lots of compounds that are going to work here. It would be very difficult for me in a video format to draw all of the possibilities, so I'm going to pick a couple that I think make good points about induction, but they're not like the only examples or even the best examples. I think they're just a helpful thing for us to look at. You are more than welcome to communicate with each other about your structures, bounce ideas off each other, check your work with each other. Well, what do you think? This is what I proposed. Do you think it would actually work given what I saw in the video? You can use the discussion board for this if you'd like, but having that conversation, I think is helpful. So I know what I need to do is to actually increase the amount of induction or increase the inductive effect. And I know that there's a few ways I can do that. I can exploit additivity. Right, I could add more than one acceptor, or I could increase the extent of polarization of this bond that starts the ripple. So I could choose a stronger acceptor. That's another strategy. Or I could somehow try to reduce the distance between the inductive acceptor and the position that I'm trying to influence. So in this case, it would be like the negative charge on oxygen, say, or still on there. Or reduce distance. Any of these strategies, or combinations of them if you're feeling very creative, any of these strategies will work. So for instance, if I dealt with additivity, I could just use 2 chlorines, something like this, and then keep the rest of the structure the same. So my corresponding conjugate base would look like that. And so I'll bring the pKa values in for these structures at the end of this section, but we can also talk about other kinds of structures as well. So what if I made a stronger acceptor? So here I want to think about a group or an element that will exert a stronger pull on the carbon than a chlorine will. So let's see, focal Nabersh. So, well, the nuclear weapon here is fluorine. So I could do fluorine instead of a chlorine. That would give me a stronger acceptor. My corresponding conjugate base would be that. Or I could think about reducing distance. So again, this is the compound I was starting with. So I could try to make the chlorine closer to the oxygen. One way to do that would be to remove the CH2 group. So I could also do something like this. Whereas my conjugate base would look like so. Okay, so this was our original structure. The idea was to increase the inductive effect by either making or using a more powerful inductive acceptor, so in this case a more electronegative element than chlorine, We could also exploit additivity, so introduce more than one chlorine, and that will get me more accepting than just one chlorine atom. Or I could reduce the distance between the oxygen where charge is building up and our inductive acceptor of chlorine. So in this case, that's what I've done by removing the CH2 group. So what I'm going to do next is show you the pKa values for 3 of the 4 of these acids, because it turns out one of them you actually can't make. It's not stable enough for us to actually measure the pKa value. And so this bottom compound, it turns out like this and this, neither of these can be prepared with a lifetime sufficient to measure pKa's. So we don't know, but if we could measure it, I am extremely confident that this structure would be quite a bit more acidic than this one. In our additivity case, where we have the 2 chlorines, so dichloroacetic acid is the name of this compound, our pKa is around 1.3. So that's what we can see, is that adding this second inductive group is going to increase stabilization of the conjugate base, and that leads to an increase in acidity. Finally, fluoroacetic acid, this compound here, has a pKa of around 2.5. So you can see that it's a little bit more acidic than the original compound we were working with, because I've included a more powerful acceptor. So you could also imagine cases where you go crazy. You could have like 3 chlorines, or like instead of a chlorine for a fluorine swap, you could add 3 fluorines to the carbon. You can mix and match these kinds of concepts, but they're all examples of induction as you understand it. Okay, so that concludes this section of our video, and where we're looking at the impact of induction on acidity. So in this section of our video, we'll look at a very different kind of effect, where we can see our 3 acids are all hydrocarbons. There are no oxygens, there's no chlorines, there's nothing that's really remarkable in any way, at least obviously. Clearly there's not going to be any induction here, because I don't have any inductive acceptors, no highly electronegative elements, no powerful electron withdrawing functional groups, anything like that. In all of these cases, carbon is bearing a lone pair and a negative charge, so I'm not dealing with atomic properties like atomic radius or electronegativity differences, but these compounds do appear to be different in acidity, and these changes are pretty significant, right? So we're talking about 10 pKa units between these two, just with the introduction of an alkene, versus there not being an alkene there. And that's 10 pKa units, so that's 10 orders of magnitude. Or having 2 alkenes, for instance, gives me a 25 order of magnitude difference between the case where there are no alkenes. So this effect, whatever it is actually quite a bit more powerful than induction, which we saw in the previous section of this video. So why would this be? We need to come up with an explanation. It's not necessarily obvious. Maybe you're looking at some of these structures and a word pops into your mind. Conjugation. Some people also call it delocalization. But the idea that this lone pair actually exists in 2 different places at the same time. This lone pair exists on the carbon where I've drawn it, but we also know that this lone pair exists on the center carbon, that there's a resonance structure for this material, which I'll draw. All right, so maybe this resonance effect, or this conjugation effect, maybe this is actually important. So we'll start making some notes again. New lone pairs that are conjugated are more stable. So what I mean by new lone pair, it's like the lone pair I'm gaining from the proton coming off. Right, so it'd be like this H leaving, that carbon gets the lone pair. That seems to be consistent with these 2 structures. It looks like I have no conjugation here, but I do have conjugation here, and my acidity increases, which means my conjugate base here is more stable than this one. But it's not yes or no. Just like most structural features in chemistry, it's not like this effect happens or it doesn't. It's like how strong is the effect, because we can see that this lone pair is also conjugated, and yet its corresponding acid is quite a bit more acidic. So what's going on here? Well, if I actually think about my conjugation carefully, I notice that this structure has 2 other resonance structures, whereas there's just this pair. Here I'll have 3 different structures to describe the lone pair position. So I would have the so-called seagull-looking structure, and then I also have the lone pair here. So I know that these two structures look exactly the same. I'm going to number the carbons here and here. Trying to make it a little bit clearer that we're talking about the lone pair existing on carbon 5 and carbon 1 at the same time. So it looks to me like it's not only that new lone pairs are stabilized by conjugation, but it's also more conjugation is more stabilizing. And that's what we see going from our middle example down to our bottom example. So what's left for us to do then is to try to mesh this observation about conjugation with our framework. What is actually giving rise to differences in stability for conjugate bases in a first principles argument? So you can approach this in a couple of different ways. You could talk about electron repulsion here, where we're actually taking this lone pair and we're like moving it around, spreading it out is maybe a better way of describing it. And that's going to lead to less repulsion. To some extent, I think that's right. Another way you could think about this is that if this lone pair exists on the carbon here and the carbon here at the same time, how many carbon nuclei does that lone pair actually experience? It sounds like it experiences 2 different nuclei at the same time. So like double the number of protons, which remember, protons and electrons attract. On the other hand, this lone pair, it's just on the 1 carbon atom. So this concept of introducing more conjugation, what we're basically saying is that if we can take that lone pair and place it on multiple atoms concurrently, we're really both reducing electron repulsions, but we're also now introducing more protons that electron pair can experience. So we have a rationale for explaining this observation. Reduces electron repulsion and increases the number of nuclei electrons see or visit. Okay, so I just want to be clear because it's never the case that resonance feels super comfortable at this point in most students' chemistry educations. That resonance is not equilibrium. So these two structures here, it's not like sometimes the lone pair is on this carbon and sometimes it's on this one. It's literally the case that the lone pair is on both of those carbons at the same time. We draw these 2 different resonance structures because I wouldn't know how to draw a picture like this where the lone pair is here and here at the same time. No idea, right? So this resonance arrow, as it's sometimes called, the one that you draw between the resonance structures, it's instructions to the reader the same way like a comma is in a sentence. This tells me average these 2 structures. And like the average will be a single object, a single drawing. That's the actual electronic nature of the compound. So that means that I'll have like what's called a resonance hybrid that looks a little bit like there's 1/2 negative charge on the center carbon and 1/2 negative charge on the outside carbon, and I'll have some pi bonding across those 3 carbons that are involved. So this is my resonance hybrid. This is like what the compound actually is. These drawings are ways for us to actually communicate that with one another. You could also think about this in an anthropomorphized way. So for instance, I am a professor. I am also a dog parent. I'm also a hiker. So those are all like different things that I do. All of them together, and other things also, describe me. But you might want to show like 3 different pictures of me to communicate to someone who's never met me, like who I am. You might show me a picture of me in the classroom, or maybe you could show them one of these like horrible videos. You could show them a picture of me climbing up a mountain, and you could show them a picture of me being woken up at 5:30 in the morning by my asshole dog. Like those are all like facets of who I am. And if you show all 3 of those pictures, you build a composite of a person in your mind. That's what these drawings are about. They give us a composite, which will yield a structure like this, the true structure of the compound. If I do the same thing here, now I'm averaging 3 different structures together. So rather than it being like -1, -1, -1, I have 1/3 of a negative charge, essentially, on carbon 1, a third of a negative charge on carbon 3, and a third of a negative charge on carbon 5. So I'll have an image that looks a little bit like this, and partial pi bonds all throughout there. Okay, so we can see how this might be stabilizing when we start to draw these resonance hybrids, right? I've got half negative charges. I'm not localizing charge in one position anymore, and as I basically use smaller and smaller increments of charge that I'm putting on specific places, that's going to be stabilizing for both of these reasons. So resonance turns out to be a really powerful effect. Looking at this acidity data, we can see that it's clearly much more powerful than induction is on its own. And that's going to be a general result for the rest of the semester, that if we had to choose one explanation, resonance or induction, resonance is almost always going to be a more powerful effect. Because we're not talking about like moving electrons like a little bit further away within the bond. We're literally talking about moving electrons from one part of the molecule and spreading them out over multiple atoms. It's a radically different kind of concept, and it's a much more powerful one. Often it's the case that both induction and resonance operate at the same time though. So in the next section of this video, we'll be looking at another example where we actually can combine what we know about these different features for driving acidity into a single example. In our last section of the video, we'll be looking at just two different structures and comparing them. And I've given you their pKa data already, but to give you a little bit more practice, what I'd like for you to do is actually draw the conjugate bases for the structures, assuming that the hydrogens that are specifically drawn out, or the explicit hydrogens, if you will, are lost. So go ahead and pause your video and draw your conjugate bases now. So we've got our conjugate bases now. We're basically removing a hydrogen and replacing it with a lone pair. If we do that on a carbon that's neutral, that carbon will become negatively charged, which we can see in both cases. And we know from the pKa data that this conjugate base is much, much, much more stable than this one. So we've got a 25 order of magnitude difference in acidity for the corresponding acids. Clearly, there's something really powerful happening here. So we've at this point established that there are essentially 4 features that we care about. And there are more, but 4 that we'll focus on for determining acidity. So structural features. We've got electronegativity. We've got atomic radius. We've got induction. And we've got resonance. So we're going to want to parse all of these, at least initially, and we might decide that we only need to focus on a couple or one or whatever it is, but we want to at least always start our analysis by thinking one or more of these factors could be involved, and we're going to look for them. So we've got carbon versus carbon bearing a negative charge, so at least initially we can rule out differences in electronegativity or atomic radius. Remember, these are about the actual atom that has the new lone pair. We've got induction. So we could make an induction argument here. We've got an oxygen that's kind of sort of close to this lone pair versus a carbon instead. That does seem to work. This oxygen is an inductive acceptor. But one of the things that you might be concerned by is think back to the section of the video where we were looking at induction directly. How big were the pKa differences? 1 unit, 2 units, things like that, right? Here we're seeing 25 units. So it's not wrong to say that this oxygen is an inductive acceptor. I think it would just be insufficient for explaining the data. We can also think about resonance, which means that we should draw resonance structures. So for a resonance structure here, we're going to have a compound that looks very similar. So these 2 carbons are both going to be bearing negative charge. And for our structure here, I've got this. So here I can start to see something important. Initially, I might have thought, well, resonance is not important because like this structure has 1 resonance structure, and this structure has 1 resonance structure, so resonance should be a wash. But that's not exactly right. It's not sufficient to just count the number of resonance structures. it's not just the number there are, it's what they're doing. What qualities are they bringing to the game here? So quality counts. If I look at this, I'm distributing a lone pair across 2 carbons, so carbon, carbon. All right, well, distribution is good generally. But in this case, what I'm able to do is take the lone pair and essentially place at least some of that electron density directly on an oxygen. So because of this resonance structure, I now have this argument that electronegativity of the atom is actually holding on to that new lone pair. Now this is important, right? So in this case, we were able to access a new feature. Right, we're actually able to place the charge, or at least some of the charge, onto a highly electronegative atom, which, as we've established in the previous video in the series, is going to be quite stabilizing. So just remember that when you're thinking about conjugation, resonance, delocalization, all those things mean the same concept. Don't just count. Don't just say, oh, well, it's the number of resonance structures. You need to draw the resonance structures and assess each of the resonance structures using these other 3 tools, right? Because remember that resonance structures mean take all these things and average them. Well, in this case, like this structure tells me that I'm averaging in this effect for these compounds, but not these. And that makes a big difference, as you can see in the data. So we've done a lot in this video. We've introduced the concept that induction can influence acidity, and we've also introduced the concept that resonance or conjugation can have a dramatic impact on the acidity of molecules. So this will be a really important cornerstone for discussions in units 4 and 5 for the semester. So make sure that you spend time grappling with these concepts, working with these ideas, making sure that you really understand them, and also please make sure that you can draw resonance structures appropriately. I'm happy to work with you in office hours to help you if that's something that you still struggle with, but it's a very important skill that you'll need for the rest of the semester. So in the final video of this series coming up, we'll be putting everything that we have together and going back to looking at acid-base reactions again and using what we know about acidities and conjugate base stabilities to make some predictions about, in an acid-base reaction, like which side of that equilibrium is favored. And that's going to turn out to be a very valuable technique for us, both in terms of planning experiments and also being able to predict common steps in mechanisms of reactions.